Hello and nice to meet you on DevOps stage. My name is Vladyslav Fedorenko. I'm DevOps team lead at Great Tech. And today I want to share with you my own experience of building cloud Kubernetes cluster setup, what issues we met with it, and how to avoid this kind of issues in future. So my topic calls enhancing cloud Kubernetes resilience, strengthening stability and fault tolerance. A lot of you may have an experience of working with on-premise Kubernetes clusters, and you know that it can be kinda a mess. First of all, you have to deploy it properly. Usually for it is used kubespray, and kubespray have long documentations, a lot of variables and a lot of requirements. You have to set every part to the correct minor version. Your Ansible version have to be exactly as pointed in documentation, because even small minor change may break everything. This playbook runs for an hour, and if it fails, you have to start all over again. Also, for on-premise Kubernetes cluster, you have no option for autoscaling. You have as much nodes as you bought. So one of the core features of Kubernetes has gone with it. As Kubernetes is a stack of small microservices that are working together to make your application delivered, you have to deploy and administrate every of its microservices separately. You have to solve the storage issue, you have to deal with Ceph and all its daemons, you have to administrate etcd, you have to provide connection to your on-premise Kubernetes cluster that may be used by VPN, all connection directly to node, or maybe SSH tunnel, which is not so secure and not so easy as well. Cloud Kubernetes is much simpler. You can deploy it with few lines of code or few clicks. A lot of services are hidden behind cloud provider infrastructure, so you don't have to administrate your storage, you don't have to go into etcd, etc. You're just ready to go and ready to deploy and deliver your apps. But a lot of things may go wrong even with cloud Kubernetes. Let's check the typical cloud Kubernetes setup. It contains two parts. First part is infrastructure part that is written on typically Terraform or CloudFormation. This part includes VPC, the cluster itself, security groups, subnets, keys, accesses, etc. It contains everything related to the cluster itself. And the second part of typical Kubernetes setup is CI/CD part. This part delivers everything inside Kubernetes, like Helm releases, Helm charts, Helm repositories, deployments, secrets, namespaces, etc. Everything that you want to keep inside your Kubernetes is delivered with your CI/CD. Short disclaimer. In my examples, I will talk about Flux as CI/CD, Carpenter as an autoscaler, and Cilium as network driver. So, what are the potential problems of this setup? Let's talk about some real-life experience, how we broke our Kubernetes cluster and how we fix it. So, my first experience is when we have a lot of namespaces delivered in one infrastructure chart. One of the DevOps wasn't able to fix this chart because it was failed to deploy for some reason, some secret not found or something similar. And he thought that the best solution in this case is to completely delete the chart and redeploy it clearly. What can go wrong, you can ask? A lot of. Because of 5 namespaces inside this chart, after chart deletion, they all got stuck in termination phase. It was infrastructure namespaces, so all of them are not working, cluster is not working, namespaces got stuck. What can we do in this case? First of all, there is no way in Kubernetes to revert namespaces from terminating phase. If it is terminating, it's all done. You have to delete your namespace completely. So, We use Finalizer for it because Finalizer Kubernetes, which is default for namespaces, will wait for every resources inside the namespaces will be finished gracefully, which will not happen in most cases. So you have to set Finalizer null for these namespaces and wait for them to be deleted forcefully. After everything is deleted, you can redeploy your chart to bring your namespace back. You will experience a lot of issues, especially if you have some separate models with IRSA service account, some additional resources that are not delivered automatically, you have to reapply it. But the worst case, if you have some manually created parts, for example, someone created secret and forgot to put it into the code. So you have to troubleshoot for everything to start back, even if CI/CD is already working and all namespaces got back. Second real-life example of disaster. We upgraded Carpenter and Carpenter CRD changes, but unfortunately we used incorrect CRDs for previous versions. They did not convert automatically and every custom Carpenter resources got stack phase. We have no running node claims and all them are failed into not ready state. So basically we have the whole cluster of not running nodes, not ready nodes, and we have 2 Carpenter pods in pending states. What can we do in this case? Thanks, we had node pool that is not controlled by Carpenter. So I use this node pool to start Carpenter pods. Then I roll back Carpenter chart to the previous version with working CRDs, reapply CRDs manually with needed version of it, and then I got Carpenter running. That almost success. With running Carpenter, he was able to see why nodes are not ready and replace them with new nodes. Cluster fixed. Third real-life example of disaster. We had Flux running in our cluster, but one of the DevOps accidentally bootstrapped Flux with 2 different repositories, 2 different folders and 2 different versions. That's why a lot of resources become incompatibility with each other and everything stuck and started to delete. The worst thing that Cilium was deleted as well, and Flux is unable to start without Cilium, while Cilium is unable to be delivered without Flux. What to do in this particular case? First of all, you need to restore your network, because without network, nothing will work properly. To restore Cilium, as we are unable to deliver it, we have to apply Cilium manually. We had the time Cilium deployed with Flux, so we used kubectl apply file with values to bring Helm chart back. And when Cilium started, we suddenly was able to start our Flux. But Flux was unable to redeploy Cilium chart, as new Cilium chart was not controlled by Flux. So to fix this issue, you have to fix the annotation on your Cilium chart to bring it back under Flux control, and with all properly annotations, Flux will see this chart back and will redeploy it in proper way. And the fourth example of disaster we met is related to Kyverna, mutation admission webhook. What is mutation admission webhook? It is Kubernetes entity that validating or mutating every resources applied to the Kubernetes. When our node gone that hold Kyverna, we were unable to start any deploys because Kyverna service was not found and Kubernetes is trying to validate deploy somehow and unable to. How we solve this issue? To solve this issue, you have to manually, using kubectl, delete the mutation webhook which is related to Kyverna service. After that, you have to deploy your Kyverna back, and it will bring the webhook back, and then you will be able to restore all your workloads. After all this disaster survived and restored, we made the conclusions and tried to point what in our setup can be broken and what is the target that we have to achieve. To summarize, we don't want our CI/CD to deliver namespaces, because namespaces don't change often, they're running for years in some cases, and we don't want to Helm chart deletion lead to this stuck problem. Secondly, we want separate node pool to run all our infrastructure components, including Carpenter. During the disaster, we didn't have one, we just had a node, a Fargate node, which was used for different workload, and thanks God we had it, so we were able to fix everything quick enough. Thirdly, we want to avoid chicken egg problem with Flux and network driver. We want Cilium to be delivered in different way, not with Flux. So we can restore Flux and it will restore apps. Here is the conclusions of what I said. CI/CD will not deliver components it depends on. I'm talking about Cilium. Autoscaler is running on separate nodes. And application will be redeployed quickly in case of everything deleted and everything got back. Let's dive into all our components. I will describe all components separately. I will tell some short summarize about these components and how we deploy it, and what we did to avoid disasters we had before. Let's start. First component I want to discuss with you today is Carpenter. Carpenter became really popular last years, and even AWS support in some cases will suggest you to install Carpenter to your clusters. Why is it so popular? It's cost efficient, it allows you to deeply customize your workloads, and it actively developed and bring you features almost every month. So, what are the core concepts of Carpenter? First concept is node pool. Node pool bring you a possibility to create specific set of nodes for your workloads. You can choose minimum instance generation, you can choose node family, either CPU optimized or memory optimized or general ones. You can choose architecture like ARM or x64. Also, you can set limits for your node pool, so it will not become too big, or if you have some metric scrapper, you will be notified about it. So you can either downscale your app or increase limits. Node classes. Each node pools are pointing to node class. You can use one node class for all node pools if you don't need deep customization, or you can create different node pools with different node storage, different node image, etc. In most of our cases, we are using Amazon Linux too, but you can create Ubuntu or CentOS or any other node image that is supported by AWS. Third concept is node claims. Why I like node claims so much? In the past, I had to work a lot with Azure Kubernetes, and my question always was, why there is such great representation of node pools in Azure and it's so non-obvious in AWS? Because in Azure you can look at your node pools separately, you can choose instances for each node pool separately, and you can delete or redeploy each node pool separately too. But in AWS you have all your nodes in one places where is not so much useful information for your daily work. You can see IPs, version of Kubernetes, container D runtime and image, and I guess that's it. When you're checking node claims, you can see all nodes sorted by the node pools. You can see this node's capacity and its type. So you can quickly look at your node claims currently running in cluster and understand if apps become too big and where is the problem is, where is a lot of not ready nodes, which is much more useful. The second thing why I love Carpenter. I had to work in a big video streaming company, and downtime was really critical there, because if video streams are not available for longer than 2 minutes, the customers are starting to type your manager and you what's going wrong, please tell me what's going wrong, how quickly you can fix it, etc. But we had to upgrade our Kubernetes clusters. So only thing we can do is to press button upgrade cluster and pray. Because only God and Azure Autoscaler knows how long it takes. Autoscaler will create new nodes, then it will try to upgrade old nodes. There will be few reboots, few application redeployment on new nodes, and it may take up to an hour. So, we invented a new way to upgrade Azure Kubernetes clusters. It was like this. First, we upgraded the control plane. After that, we created all node pools identical to the old ones we had, with the same capacity. Then, we manually move all the workloads to the new nodes, checking that everything is running fine. Then we drain all nodes and delete the old node pools. This method allowed us to reduce the downtime to 1 or 2 minutes, which takes only to start the apps on the new nodes, and it was great, it was game changer. But with Carpenter we don't need such things anymore, because Carpenter has its own amazing mechanism called drift. You just simply upgrade Kubernetes control plane, then Carpenter sees that control plane version is different from your node version and drain your nodes one by one, delivering new ones. You can control your drift. You can set budgets, how many nodes can be drained at the same time. You can also mark application as do not disrupt, and this application will not be moved away by Carpenter. You can upgrade it later manually. Also, you can set the time where you prefer your drift, and before this time, all your workloads will be on its place. Besides of drift, there is also useful consolidation Carpenter policies. Let's talk a little bit about them. First one is when empty policy. When empty policy is good choice when you have downtime sensitive application, so node will be disrupted only in case when there is only daemon sets left. You can also set consolidate after timing. In that case, Carpenter will wait for some seconds or minutes before drain the node. Second type of consolidation is when empty or underutilized. It is good for cases where you have a lot of replicas of your application or your application is not so downtime sensitive. So Carpenter will always choose the cheapest nodes to run on. That is the most cost efficiency way to run your workloads, and is a great choice for general node pool. Expire after is a security feature for consolidation. You can set the expire, for example, 1 week, and every 1 week Carpenter will replace your nodes with new one. That is very useful if a new node image was released or new vulnerabilities were found in the previous one, and you always will have fresh nodes running inside of your cluster. The first feature is spot-to-spot consolidation. It is still under the alpha testing, but if you run spot node pools in your Kubernetes cluster, you can try it. The Carpenter will not wait for spot to expire. It will also try to find the cheaper alternative of your current nodes and install it if possible. From my own experience of using spot-to-spot consolidation alpha feature in Carpenter, I can say that it works good. It will slightly reduce your costs on your spot node pools, but you have to notice that Carpenter may disrupt nodes too frequently, and in this case your application will start flopping. To avoid this issue, I highly recommend you to lower the budgets for spot consolidation nodes. I set it to 1 node in 5 minutes and no more. In that cases, everything is moving gracefully and you will not observe huge service interruption. How we deploy Carpenter and its entities to our Kubernetes cluster. We use default Terraform resource called Helm release. You can see a screenshot from official documentation on my slide. But the way suggested by HashiCorp has some disadvantages. If you include the whole values YAML file, you are not able to point output to another Terraform modules. And if you use set name value away, your code became too big and not much readable and not so easy to administrate. So for all our infrastructure Terraform Helm releases, we use template file function that pointing to YAML files. What are the advantages of this way? We can use readable YAML files with variables and specific or outputs. We set these values there, so it is easy to check that everything in YAML is on its own place, and we also are able to create resources with cycle. To create similar resources with cycle, we use kubectl manifest Terraform resource that goes through our locals, coalesce with default ones, and replace them with specific ones needed for some node pools. In this case, we avoid a lot of boilerplate code because all these resources, node pools as well as node classes, are 90% the same. You can see the examples on my slides. To deploy AWS part of Carpenter with all needed permission and policy, we use Carpenter module for AWS official Terraform resource. There is a lot of inputs besides of defaults one. You can create your custom policy for some node pool if this node pool needs to reach some external resource like AWS S3 bucket or AWS Athena or anything you need for your application to work properly. For another nodes, you create just default policy or default instance profile, which is both available options. To control Carpenter node pool limits, we use a simple Grafana dashboard that parses Carpenter metrics and post in real time the current usage, the current limits, how many percents of usage we already reach, and also you can set different and other values from Carpenter metrics, for example, what availability zones pods are running in, or how many pods are running in specific node pools, etc. I talk a lot about separate node pool for Carpenter, and here on this slide you can see our example of this setup. You can either choose self-managed node pool or Fargate node pool, but we choose just this managed node group as enough solution for us. These nodes are not registered as Carpenter node claims, obviously, because Carpenter can see these nodes and cannot delete them or drain. We didn't add autoscale group to this node pool, we just calculated how many infrastructure workloads we have, so we choose that 2 M6A large nodes will be enough. Additional note that you will not able to use Carpenter drift mechanism to upgrade this node pool, obviously, as it's not controlled by Carpenter. So to perform upgrades, we just manually do it in AWS console during the whole cluster upgrade or another maintenance window. And with this use case, we always have an entry point for our workloads, and we have the nodes that will never be disrupted until we do it manually. To summarize about the Carpenter. First of all, as I told before, be sure that Carpenter is running on separate node pool, not controlled by itself. In this case, you will always be able to restore Carpenter pods, and everything else it will restore by itself. Secondly, Carpenter is actively developing project, and the things are changing often, including CRDs or Carpenter entities. Be sure to read changelog twice and read all breaking changes before you start the upgrade. If it's possible, upgrade stage environment first. Third thing, Besides of Kubernetes part, Carpenter has its own resources in AWS. They are needed to deploy new nodes and attach them to Kubernetes cluster. Be sure that all needed permissions are granted to Carpenter's service account. Let's talk a few words about Cilium. We deployed Cilium a long time ago to solve the issues with default Amazon CNI plugin, which had a problem with releasing free IP addresses after not go out. Cilium solved our problem, and then we discovered that there are a lot of useful features too. First feature, of course, is eBPF routing, which allow you to route with Linux kernel and decrease the latency of your apps. We use Cilium as kube proxy replacement to lower latency in our apps and achieve even better performance. Second feature is Hubble. Hubble is the separate part of Cilium deployment, which can deliver you a good observability of your network. You can choose the namespace and watch in real time what are the network relationship inside your namespace, what pods are trying to achieve the world, and what pods are communicate with each other. Also, you can block some unneeded accesses with Cilium network policy, and you will also see all blocked connection in the real time. How we deploy Cilium? As I told before, we choose to move all our core Kubernetes components to Terraform code with our cluster, add-ons and Carpenter. Cilium is deployed there as well. We use the same setup with Helm release Terraform resource. We create YAML template file and use n-specific variables in this file to set it up. You can see my setup on the slide. Cilium CLI. Cilium CLI is a useful feature if you want to see your current Cilium health, what image are used in your cluster, if you want to check what errors are currently observed. Also, you can do pre-flight checks before you upgrade, and it is highly recommended by Cilium team. With pre-flight check, you can see if everything is already up to date with the next Cilium version and if you are ready to go. Kyverno and namespace problem. As I mentioned at the start of my speech, if Flux is delivering namespaces, it may lead to problems. If Flux is broken in some way, for example, CRDs are deleted accidentally, or Flux bootstrapped from few different folders, or upgrade gone wrong, your namespace may be stuck in terminating phase. How to restore from this? You should delete your namespace completely by using finalizer. You should delete Kubernetes finalizer, set finalizer to null. That will drop namespace completely, and then you will be able to recreate that. As namespaces are not the entities that are changing often, and sometimes they are running for years, we choose to deploy namespaces with Terraform as well. So we created the small module that creates namespace in our cluster and calls this module for every time we need a namespace for our app. With this setup, we were able to deliver all the labels, common labels and per-app labels, and suddenly we have every correct text for every namespace. But how can we copy these labels also to our deploys and resources inside the namespaces? And this is Kyverno's work. What's our setup? We have few Kyverno's policy. First one is taking namespaces labels and put them into the deploys and PVCs. That's how we have everything in every namespaces tagged correctly. Second part is taking labels from PVC and put them as annotation. How we use this annotation? We use small deploy called Kubernetes PVC tagger. This deploy is able to export PVC tags into AWS tags. by special annotation we create before. Let's have a look on our setup. Here is you can see two policies. The first one that actually take namespace labels and put them to deploys in PVC. The second one is the one that create annotations for our tagger. As you can see, policies on Kyverno are pretty simple and readable, so we are able to use it somewhere else in our cluster, and Kyverno become important part of all our setups. What Kyverno can do also, besides of modifying your resources with admission webhook? Kyverno can create best practice policy. We use policy for mandatory resources and limits. We use policy for mandatory liveness readiness probes, and also we use security policies that throw warning when you're trying to run your container as root. Besides of that, we can use security policies that will forbid users to create some unwanted resources. For example, you don't want to see empty ingresses in your cluster because it may break the entire ingress class, or you don't want users to create public ingresses in your cluster. We can forbid it with Kyverno easily. To simplify Kyverno administration, I suggest you to use Kyverno Policy Reporter, which is useful graphical interface for Kyverno. As you can see on my slide, there is a good visualization of Kyverno policy statistics. You can see how many your deployments are not following your best practice policy. You can set your best practice policy as audit. In that case, you will just receive the warning during pod starting. But if you want to completely forbid to deploy some type of resources or some resource properties, you can use policy enforce. In that case, admission webhook will block any attempt to do so. What is the potential problems of Kyverno? If you have Kyverno deployed in your clusters, the admission webhook should be available all the time, because if it will be unavailable, every deploy will fail to start. In this case, you have to either mark your Kyverno to be not disrupted by Carpenter, or in our cases, we just move Kyverno on our separate node pools, untouchable node pool, besides with Cilium operator and Carpenter. That's why it has 100% uptime. So let's go for conclusions for my resilient Kubernetes setup. First thing we did, independent infrastructure component. We deploy all our components separately. Carpenter, Cilium, Flux are separate parts deployed with Terraform codes, besides with Kubernetes add-ons. So we don't have depends on our CI/CD to deploy our infrastructure. We use CI/CD only to deliver apps and apps Helm releases. Secondly, we moved our namespace to Terraform as well, because we think that namespaces are not changing often and we don't need to continuously deliver them. That's why we created this code. In case of Flux fails, we will restore our apps quicker, because we will not have stuck namespaces, and all we have to do is just to reconcile our release or redeploy our releases, and apps are ready to go. Third part is separate node pool. It is our important entry point for disaster recovery. We always have two nodes that keep Cilium, Kyverno, Carpenter and other important components. Even if everything in cluster is broken, you have this two node where you can start from and deploy everything else. And the fourth part is disaster recovery plan and training. You have to understand how to restore your components, When you didn't break everything for a long time, there may be a lot of manual created scenes, manual created secrets that will not deliver back, and you will have to fix it by hands again. So keep everything in code, use best GitOps practice, and perform DRP training when you are able to. So that's it. Thank you very much for your attention. I hope my speech was useful for you and you learned something and you will be able to avoid our problems and mistakes in future. If you had some similar problems or similar stories, it would be very interesting for me to hear how you solve them, what are your own personal solutions, so add please my personal LinkedIn and you can DM me to discuss any of these cases. Also, please subscribe to our Great Tech social media to be connected for our upgrades, and if you want to join our team to build best iGaming solution, you can check our vacancies. Thank you for watching. Have a great day. Bye.